is that we're going to talk about the incline plane. Now, what I'm going to say here is this is considered one of the most important problems in Physics 4A. The incline plane problem. I would say it's one of the most iconic problems in Physics 4A, without a doubt. Everybody assumes you know how to do this, okay? You know how to do this when you walk out of 4A. So what I want to do here is that I want to use numbers, and I want to look at this, reasonably here. So what I want to do here is that I want to look at the forces on a block where the block is stationary on an inclined plane. And I don't want to bring friction into this place here. So what we want to do here is that we want to, so suppose we have a stationary block on an incline. So when I draw this out, I'm thinking this type of thing. It looks like this, right? Here's my incline. I'm going to even give it an angle because I want to deal with this with numbers. So now what I'm seeing here is I got a block. So here's my block. And so when I'm looking at my block here, in order for it to be stationary on a frictionless surface, what I'm imagining here is that I have tension in a rope. Okay. So what I'm saying here is that on the surface right here, this is frictionless. So it's the tension in the rope that's keeping this block stationary. And so what I'm going to say here is I'm going to say that the mass times gravity here is then going to be 5 newtons. And what I want to do here is that I want to determine all of the forces acting on this block. So our goal here is that we want to determine the forces acting on the block, which implies the normal, right? The normal is really the main one, but what we're going to do here is that we're going to look at the normal and the weight on the incline. That's what we want to do here. So one of the things that we know here is that as soon as we say that this thing is stationary, we know that we must have balanced forces. And from some of our previous discussions, I stated that it was best to choose a coordinate system where the motion of the block is along one of the coordinate systems. But in this case, because it's moving along the incline, we really want to choose the axes along the incline. Okay, so what I'm saying here is that from previous discussions, it's best to choose a coordinate system where the motion lies along one of the axes. So when you look at the coordinate system, you could choose a coordinate system that's sort of like the standard coordinate system, right? So when I'm looking at this coordinate system here, you could choose a coordinate system that goes like this. And what I'm saying is that this is not a good coordinate system, right? Not a good coordinate system because any motion will not be along one axis. So a better choice of a coordinate system would be to choose it in such a way where you do have motion along one of the coordinate systems. So in this case, this becomes the better choice. So this is the better choice. Problem. One now has to deal with the components. And what we want to do here is that we want to sort of like look at a couple of things here. So the first thing that you want to remember here is that anytime you have a triangle, the sum of the angles must be 180s. Okay, so this is just a reminder that the sum of all angles in a triangle are 180 degrees. So what I want to do here is that I want to go in and I want to look at the free body diagram and then start thinking about what actually happens here. So what we want to do here is that we know we have balanced forces, so all forces have to balance out in length. Okay, so here we go. What you're going to find here is that there are two choices in dealing with the angle. And what you're going to see here is that when you look at physics, they typically only deal with it one way. The problem is more students get really confused when they do it the physics way. I learned the physics way, but after teaching for 24 years, I realized that people actually don't like that method. Why? Because there's more mistakes that happen when you deal with the physics way. So let's deal with the physics way first. So let's call this case 1. So every physics textbook does it this way. Okay, and this is physics way. And what we're going to do here is that when I look at my incline, what do I see here? Well, my incline does the following thing here. I have an incline. And the physics, they deal with they use the angle equal to 37 degrees. So let's look at that scenario. So if I look at this scenario here, and I'm looking at my block here, what am I seeing here? Well, I'm seeing this. I'm seeing that because this is in static equilibrium, of course, all forces have to balance out. So when I look at this, there are three forces acting on the system. One, there's the normal force, there's the force of gravity, and there's the tension force. Okay, so when you're looking at this thing here, what physics does here is it starts to then play the game of what the angle is. So what we do here is that we do the following thing. So what I'm going to do here is that I want to break this into components. Okay, so we're going to, let me do this a little bit better. So we're going to say we're going to break into components. And as I break this into the components here, what I'm going to do here is that I'm going to choose my axes that looks like this here. Okay, so as I draw my vectors, this is what I'm seeing here. I have a weight vector that looks like this. This is the magnitude of this. And if I choose this to be my positive y, and I'm going to choose this to be my positive x, it doesn't matter the direction that I choose it. Look what I'm going to do here. The first thing I'm going to do here is I got to break these guys into the components. So you're seeing here that this guy is minus gx. This guy over here is minus gy. Okay, of course, I have my normal, and that has to equal mgy. And then I have my tension, and because everything's in equilibrium, it has to be like this here. That's my free body diagram right there. Now, let's be more careful here. So note, because gravity goes down, gravity, the vector mg has to be what? Now let's be careful with our angles here, right? Let's look at the angle. So this guy here is a right angle. That guy is a right angle. So we know that's 90. And of course, this angle here is 37 degrees. So wait a minute, if that's 37 degrees, then we know for a fact that the angle along the x direction here, that is this angle right here, we could see here that the sum of the angles must be 90 degrees, must be 180, or these two angles have to be 90, but let's write 180, so it's 180 degrees equals 90 plus 37 degrees, plus this angle along the x direction. And look what I'm going to do here. I'm going to do something a little bit wicked and call that theta x. So when you calculate theta x, you find that theta x is really what? It is an angle of 53 degrees. So in other words, the angle along the x direction is 53 degrees. But then check this out. This angle right here, because we know that that has to be a right angle, that angle cannot be 53 degrees. It has to be 37 degrees. So this angle here is 37 degrees. So when physics deals with this thing here, what they do here is that they redraw this thing. And they don't use the 53 degrees here. What they do here is that the angle 37 degrees is measured relative, I got to move this down a little bit, relative to the y-axis, not the x-axis. Well, that changes quite a bit. So when I look at my triangle, this is the way physics does. they're going to take this picture right here, and I'm going to bring it down. I want to paste this guy in here. What they do here is that they come in here, and this is what they write. They write mg, and then they say, okay, this guy is going to be mgy, and of course this is going to be mgx, but the angle of choice here is this angle, which is 37 degrees. So anytime you measure an angle relative to the y-axis, if you're not used to solving triangles and you just try to memorize things, then the sine and the cosine are switched. Okay, because of this reason, right here, we find that the sine and cosine are switched. And you might be going like, what the hell do you mean by that, Carlos? Well, what it means here is that when I look at mgy, oh no, excuse me, mgx, it should be mg sine of 37, and mgy is then going to be mg cosine of 37. Most people think that the x component is always cosine and that the y component is always sine. That's what I mean by doing this. Now, if you see this, it's perfectly fine, and you are in tune with physics textbooks. Because in fact, I think 100% of the textbooks actually do it this way. Okay, so doing it this way is totally legit. Problem. My experience of 24 years at Cabrillo tells me that's what most students don't see.
Hey, Carlos, I had a quick question. If
Sure.
we ended up using 53 degrees, would we switch to sine and cosine back?
Then you would say, since 53 is measured relative to the x-axis, then it's cosine. So yes, you would just use that process here. And my job here is to do what? Is to give you options. If that works for you, that's fine. And so what I'm saying right here is this. There is another way to do this. And we've actually already talked about it. So this is my case 2. And in this case 2 here, what I call it here is I call it translating the angle 37 degrees. So what we did here is that we did the following thing here. So what you're finding here is that it really comes down to this picture over here. So if you look at this picture right here, that's really what we want to do here. And what we do here is that we translate the angle 37 degrees to be measured relative to the x-axis. But we did that already. And what I'm saying here is that let's go back and look at this thing here. And what we did here is that we did the following thing. So if I look at my free body diagram again of this thing, what do I see? Well, I see a tension along this direction. I see mgx along that direction. I see a normal like this, and then I see mg. Why? Where this guy is this guy right here. This guy right here is mg. So when you're looking at this thing here, and I start to sort of like draw out my triangle, we agree that that's 90 degrees. This angle here is 37 degrees. And this angle is 53 degrees. So so what that tells us here is that now that the angle is measured relative to the x-axis here, you're seeing that the angle relative to the x is 53 degrees. So many people then say, oh, wait a minute. If it's along the x-axis, as we're showing right here, then what this implies here, that the weight component now read what? Well, they read along the x-axis. So if you're the kind of person that go like, oh yeah, x is always about cosine, then look, you can still do this. And along the y-axis, you go like, yep, that's a sine. You could come in and you can read exactly like this here. And when I started doing this about 10 to 12 years ago, I found that people did a better job. That means there was less mistakes in free body diagrams with inclines because they were able to translate the angle into a form that worked for them. So my experience tells me that most students, not all, most students prefer this form. So if you're of this form, then your job here, number one job, is to do what? Change your angle so that it reads relative to the x-axis. Okay, so if I do that, you're going to see here is that here's what you're going to find. That so in summary, if this is what you're going to see here, you're going to see that if I write mg, so if I can write mx two different ways. I can write mgx, either mg sine of 37, or I could write mg sine of 53. And you know what? Oops, sorry about that. Cosine of 53. And if you compute that number, you know what you get? You effectively get the exact same number. In this case, it's 3 newtons, no matter what. And if you go calculate mgy, you could use the 37 degrees, or you could use the 53 degrees, and you're going to find here that this gives you the exact same number. So you choose what works for you. So now, with this in mind, I want to go in and I want to look at what the free body diagram tells us here. So here we go. So now I'm going to apply N2L to the block. So if I apply this to the block here, what am I seeing here? Well, I'm going to choose my downward direction to be positive, right? This is what I chose right here. So if I come in here and just remember, it's already written on your notes. I'm not trying to have you do more work here, but this is how I chose my free body diagram. So if I choose this here, what am I seeing here? Well, I'm seeing that the sum of the forces in the x direction, look at mg, it's positive. I get mgx in the positive direction. And then I'm going to get what? I got tension. And because it's in equilibrium, this is 0 here. And so then if I look in the y direction, then I could see here that this is going to be plus the normal minus mgy, and that has to be equal to 0. So now the choice is yours. If you choose, depending on how you choose this, we can see here that the tension in this case could either be mgx, which could be, let's say, mg cosine of 53. Since I just put that number there, that's going to be 3 newtons. If I look at the normal, I can write mgy, which then is going to be mg sine of 53, and I'm going to get 4.0 newtons, right? I get those components right there. That is the inclined plane. So what I'd like to do here is I'd like to interpret this before moving on here. So I want to do an interpretation because there's something really beautiful about the inclined plane. And what I want to say here is that let's start with the block on flat ground. So suppose the block lies on flat ground. So when I'm looking at this thing here, here's my block. And so what I'm seeing here is that with this block, what we're finding here is that when I look at the normal, of course, that normal is flat, and then the weight has to be exactly the same size. That is the weight. And what you're seeing here is that when you look at the normal in this case here, we can clearly see that if it's static, then we have to have the flat equal to mg, and mg in this case is 5 newtons. So we know that for a fact. So the weight is interpreted to be a scalar. So most people read this as a scalar, right? Slash number. Because weights scales are not associated as a vector. But weight is a vector. That's the problem. It is a vector. And so what we want to do here is that now we want to look at the incline. So now let's say that we place the block on an incline, on a weight scale. What does it read? So now I have my incline. And of course, this angle is 37 degrees. So when I'm thinking about my weight scale, here's my weight scale right here. And now I have my block on it. So when I'm placing my block on this thing here, what do we know here? Well, when I remember, it's stationary, it's not moving. So what you're seeing here is that now the normal is different because we know that the normal has to handle what? It has to handle mgy. And there's also an mgx component. So now what happens when we can do this? So when you do this, we cannot ignore the vector nature. And what it says here is that the incline does not support the full weight, but part of the weight. So you could see here is that the weight scale reading is going to be, incline has to be mgy, but we already saw that mgy was 4 newtons. So this immediately tells us that n flat is not the same as n incline. The weight scale reading is different here. And so what you're seeing here is that what this tells us here is that the n incline value does not support the full weight of the block. It doesn't support the full weight, but a partial weight. And the question is, how can that be? Weight is a vector, not a scalar. It is not a vector, it is not a scalar, it's a vector. So what you're seeing here is this. You're getting part of the weight is distributed where? Parallel to the surface. Right? And the way we look at that thing, because look, part of the weight is along the x direction, which is 3 newtons. And then you get part of the weight is distributed where? Perpendicular. To the surface. And when you look at this, you're getting mgy as 4 newtons. One has to admit that this is quite strange to think about weight distribution along 2 directions, right? Is this strange? Hell yes. Think about it. It's quite strange to think about weight distributed along two directions. But it is. And how do we actually get the weight of the object? The weight of the object is equal to mg. And because mg is a vector, it should be mgx squared plus mgy squared square root. And when you do this, you get back the 5 newtons. Very, very unusual. But that's what it means to put an object on the incline. Its vector nature shows that weight is being distributed along the parallel and perpendicular components. Very, very, very odd indeed, but super cool nonetheless, right? You gotta admit that is really, really cool when you think about this.